Uh, so first, I will introduce the first speaker in the afternoon. The speaker is Will Bogaerts, coming from Ghent University in Belgium. He is an IEEE fellow and a senior member of OSA and SPIE. Yeah. So he will talk about programmable photonic circuits. Okay, please.
Thank you very much. Um, yes, I'll be talking about programmable photonic circuits. Um, First of all, I'm very grateful for the award that we received here at the International Congress on Basic Science, um, the Frontiers of Science Award in the field of image and signal processing. And I'll try to frame it a little bit also in that context. Um, the paper that triggered the award, or for which the award was awarded, is actually an overview paper and a kind of a perspectives paper on the field of programmable photonic circuits. And it was not just by myself, it was written with quite a few other people that are really leaders in this emerging field of photonics. And I'll sketch that later on in a much more detail. So, but on behalf of all my co-authors, I would really like to express my thanks for this award that we received. Now, let's talk about the topic itself. If you look at it, programmable photonic circuits, let's break that down. It's a simple title, but there's still 3 words, and what is the context of those words? Well, if we think about circuits, I think most people will think about electronic circuits, like wires where electricity or signals flow, and you can basically do information processing or power transfer. Like all our electricity works that way. If we think about photonic, that comes from the word phos in Greek, means light. It's similar to optics, where we manipulate light, but when we think about photonics, we think about manipulating light on a small scale, quite often on the surface of a chip. And then programmable, we're quite familiar with programmable objects in our world. All our smartphones, computers are programmable. We have programmable toys. Now our cars and our houses also become more programmable. It means that we can configure the functionality of a device in software. So there's a software layer that controls how a device or how a system is working. So if you take all of these together, so manipulating light on a small scale, connection of things functional building blocks, and configuring functionality in software, and you rearrange the words a little bit, then with programmable photonic circuits, we try to configure connections of light on a small scale using software algorithms. And why do we do that? Because light contains information, and we can use light for information and signal processing. Now, if we think about how to do computing or information processing with light, we already know how to do that very, very well with electronics. Electronic circuits basically are very, very sophisticated. You can do a lot of information processing with them. And one of the things that makes electronics so powerful is that you can actually have very strong interactions between electrons. They're fermions, they have a charge, which means that you can make very, very nonlinear functions, which makes electronics extremely good at binary logic. Photons, on the other hand, have a completely opposite behavior. They're bosons. If you have 2 photons, by nature, they almost don't interact. If you have 2 beams of light, you can cross them, they will not interact. So that means that they're very bad at nonlinear functions like binary logic, but they're very good at linear analog functions. And so when I talk about what we can do with photonics today, I'm going to mostly talk about functions that fall in this domain, linear analog operations. Now, what information can we take in light? If you just take a beam of light, a laser beam, for instance, like from the laser pointer I'm pointing here, what information is encoded in that beam? Well, I can switch this beam on and off. I can do digital modulation, like Morse code. Also, the beam has a certain shape, a profile, an intensity profile, can look a bit like this. It has a polarization because light is an electromagnetic wave. And it has a wavelength. This is red light, but you can have infrared light. You can have lots of information in one beam of light. And we can use that information to do useful things. The most simple way is communication, like indeed having a laser link, switching light on and off, and communicating it over a long distance. That's a very easy way of communicating. Now, if we take a beam of light and we look at a profile of light, like you basically have an electrical and a magnetic field profile, and then you propagate that beam of light, like this laser beam, through space, it does not remain the same. It basically propagates according to wave equations written here, which basically means that your beam of light will change its profile. Now, what is actually happening is that as it propagates, this beam of light is essentially solving this differential equation or this integral as it propagates. You basically, the beam of light is executing a computation or executing a mathematical integration as it propagates through space. And that is something you can use because you don't necessarily have to propagate light through free space. You can actually put objects in the way of light. A very simple way, or simple object that we all know, is a lens. If you put a lens in the path of a beam of light, and you look at the profile in the focal plane before the lens and in the focal plane after the lens, you will find that that field profile has undergone a Fourier transformation. Without any effort, it's just the propagation of light and the fact that you have a lens in the middle executes a Fourier transformation between the two focal planes. And that's normally, if we think about computations in digital electronics, that's a quite expensive operation. That here with light, you just execute without any effort. It's just the physics of light, the differential equations in which govern the propagation of light. So, and this is just the most simple transformation you can do. It's a Fourier transformation. What if you can do other transformations? Yes, you can. You can basically manipulate light in many different ways. You can do it with multiple stages on. You can do it with multiple stages on a breadboard or on an optical table. Or you can do it with what we call spatial light modulators. In that case, you do, for instance, put a bunch of pixels, like an image, a pixelated image, before a transformer object, and then afterwards you use a photo detector or a camera to see how the object has transformed this pixelated image. So instead of a continuous image, you just pixelate it. It becomes discretized. So you have kind of a digital input, a transformer object that could be a lens or could be something else, and an imager that basically records, again, a pixelated image. You can do a lot with that. We have these devices. We have spatial light modulators. It's typically what you have in a projector, the overhead or the beamer that we use to project things, and the cameras we also know. These are objects that we already have at our disposal. For instance, if you take such objects, like you take spatial light modulator, like something that generates an image, a lens, then you take a second spatial light modulator and another lens, and then a camera. What you execute here in this simple optical system is essentially a convolution. You take this image, you convolute it with this kernel, and you record here what the convolution is. The nice thing is that this computation basically itself does not consume any energy. It just requires the light to propagate from here to here. So all the transformations, all the matrix operations that are actually happening to execute this Fourier transform, then the multiplication with the kernel and the other Fourier transform, they basically happen just with the propagation of light. And this is interesting because you can use this to do computations of light, to do image processing with light without much computational digital overhead. Now, if you want to generalize this type of functionality, you need, in the center, you need an object that basically can do any kind of transmission matrix. So if you want to do these general transformations, instead of just doing a convolution or doing a Fourier transform, but you want to do any general linear transformation, you need some programmable object in the middle that can implement this transformation. Now, if you can do that, the number of, essentially, you're doing a matrix vector product or a multiply accumulate operation, the amount of floating point operations that this system can basically represent scales with the square of the number of inputs and outputs. And if it's a large image, that means you have a lot of computational power at your disposal. Now, the way to implement such a general object in the middle, there have been multiple ways to suggest it, but the simplest way, and the first one to actually propose it was already in the 1990s, was by REC. You basically need only two types of objects to do this. You have phase shifters that cause a little bit of phase delay of the light. So it did delay the optical wave a little bit with a controlled amount. And then beam splitters, which basically allow you to split the beam of light with an arbitrary splitting ratio. And if you organize them in such a triangular matrix, and you come in with a beam of light, you basically pixelate the beam of light when it enters the system. And what you get at the output is, again, a pixelated beam of light. But there's between this one and this one, you have an arbitrary unitary transformation, which you can fully program by programming all the splitting ratios and all the phase delays of the system. Now, this concept was basically proposed in the 1990s, and then basically no one did anything with it until in 2013 it was revived by one of the co-authors of the paper we wrote, David Miller. And he basically came up with an extra clever idea to put like kind of detectors in the middle of this system, which allows you not only to execute an arbitrary unitary transformation, but also very easily configure such a transformation and optimize such a transformation. And I'll give you some examples later. Now, again, if we come to this, you can manipulate beams of light with lots of different elements on a chip. But if you want to make a really complex system, it rapidly becomes very, very difficult to do. If you put it on an optical table, your optical table fills up quite rapidly in a way that it becomes unmanageable. Especially if you want to put this kind of computation in a data center, it's hard to say, for instance, that we're going to put the data center full of systems like this. So we need something that is more easy to handle. This is an example, another example of an experiment like that, where in this case it was done for quantum computing, but it's a similar setup with lots of hundreds or even thousands of optical elements on an optical table. Not practical. The obvious way to do it is basically follow the same path as electronics has followed many years ago. Let's try to put all this on the surface of a chip. And the moment you go to chip-based technology, you get a lot of benefits. In electronics, we've seen that. You can get much more complex systems. Your performance is much higher the moment you integrate everything on chips. Everything becomes solid state and therefore more reliable, easier to use, smaller form factor, lower cost, etc. You can do the same thing with optics. You can basically put optics on a chip. And this is a technology that's already quite advanced, but not that widely used. We all know that there exist optical chips. Every cell phone has a camera. All the lighting today is LEDs. If you have an iPhone, you have that Face ID recognition. That's actually an array of very small lasers. But these are not the chips that I'm going to talk about. The chips that I'm going to talk about are, at this point, still not as widely accepted and widely used, or at least not in your handheld devices that you know today. They are photonic integrated circuits. And this is the type of technology that I'm going to talk about today. What is a photonic integrated circuit? It's, like I said, it's photonic, so it uses light. But it's also a circuit, which means that to describe this system, this technology, you can describe it as a set of building blocks that are connected by wires, which is typically what we also know from electronic circuits. So you have building blocks. You can abstract your system as a set of building blocks, each with their own function, connected by wires, and you get signals that are transmitted between building blocks. Except that the building blocks here are not like in electronic circuits, transistors and resistors and capacitors. No, they are optical building blocks. They are lasers. They are modulators, which are devices that transform an electrical signal into an optical signal. You have wavelength filters. You have photodetectors that transform an optical signal back into an electrical signal. And you need, of course, if you have chips, you need to connect chips together. So you need optical wires, which I think most of you will know are optical fibers. The same thing as we use to connect computers or internet devices together. So optical chips are essentially integrating all of these building blocks together on a single chip and connect them with optical wires, which we call waveguides. Now, what is a waveguide? It's essentially a stripe of material with light propagating along the material. In this case, the material has a higher refractive index than the surrounding, which allows the light to be trapped inside that core of the waveguide surrounded by its cladding. And the nice thing is, if that difference between core and cladding is large enough, is strong enough, high contrast, that means you can route the waveguide along tight bends. You can basically guide the light along bends, and you can implement a lot of functionality on a very, very compact form factor. For instance, you can do splitting of light by splitting it into two separate waveguides. You can do coupling of light. You can do coupling of light, like for instance, you couple light, you split it over two paths, and then you combine it again. The nice thing here is that this is already a quite advanced optical function, because light is a wave. It's an electromagnetic wave with a very high frequency, which means if you split a wave has high and low points, it oscillates. Depending on the path length difference between those two arms, when it combines again, it can either add up constructively or add up destructively, so you get interference. And so if you can control the phase delay here, like for instance electronically tweak how much the light is being delayed in one arm, you can choose how much light ends up in the top arm or in the bottom arm. So you effectively have an electrically controlled light switch with this. Now, it becomes more interesting if you deliberately add a delay in one arm, like adding an extra path length, which we indicate here with delta L. What you now get is, because you have two waves, the waves that arrive here will have a phase delay because of the different path length, but the phase delay depends on the wavelength of the light. So which means that for some wavelengths, the light adds up in the output. For other wavelengths, it cancels out. So what you have here is a sinusoidal transmission profile as a function of the wavelength of light. In some wavelengths, you have high transmission, low transmission, high transmission, low transmission. This gives you a way to filter out your light that basically gives you a path to select certain wavelengths in one output and other wavelengths in the other output. And that's a function that we'll come back to later. It's a very fundamental function for a lot of optical systems. You can do even more fancy ways with your waveguides. I mean, you can loop a waveguide in a circle or in a rectangle. Basically loop it around. And now you have your wave that is actually running around in that ring. If it turns out that the wavelength fits an entire number of times in the ring, then the wave going around once will add up with the wave that is just entering. And it will add up constructively. It will resonate. It will build up the power into that ring. Basically that means that it will kind of draw out all the power from the main waveguide. It will cancel things out, and as a result, you get a very sharp, very deep transmission dip. Again, a way to filter out certain wavelengths from a path of light. And if you then add a second waveguide on that ring, you can basically get the blue transmission curve. You can drop out those selected waveguides into another waveguide. So this is cool because these are very basic circuits, very basic connections between like beam splitters, couplers, and waveguides that you can already do quite complex functions. Now, to summarize, kind of, we have on our, I showed you some simple ways to transport light and to filter light, but of course we need active electrical control, so we need to generate light, we need a laser on our chip, and we also need ways to convert our electrical signals into optical signals, which we do with a modulator, and our optical signals back into electrical signals, which we do with a photodetector. And all of these we try to integrate together on our chips. Now, over the years, photonic chip technology has become more complex. It's not at the level of complexity as we have in electronics. We don't have optical chips with 1 billion components today. But we are growing to a situation where our chips started very simple to chips which now contain thousands or even 10,000 of building blocks on the same area. So in terms of complexity, you could say that photonic chips are roughly at the level that electronics was in the 1980s or early 1990s. So we actually see in photonic chips also, I mean, if you draw a plot like that, you might be familiar with Moore's law, like the exponential scaling of electronics. We see something similar in photonics. So we see that the complexity of photonic chips is really going up and up and up to 10,000 or even 100,000 of components per chip. Now, what are photonic chips used for today? Already, they are in use, mostly in high-performance computing and data centers, not to do the computations, no, to transport information. One of the nice things of optics is that using optical fibers, you can transport massive amounts of information over a long distance with very little loss. So over time, we've seen that in data centers and supercomputers, the links are gradually being replaced by optical fibers. We're no longer using copper wires for longer links, we're using optical fibers. And those optical connections are getting closer and closer to the electronic chips. So one of the big trends today is what we call co-packaged optics, is to put the optical receivers and transmitters right next to the electronic processors. And that's the main driver today for all this technology. So we see today a very big explosion in optical fiber links for every data center that's being built in the world. Basically, how does that work? You can communicate over optics very simply. You need a light source, so a laser. You need to put an electrical signal onto that light source, so you're modulating the beam. The most simple way is just switching on and off very rapidly, like 100 billion times per second, you switch it on and off. Then you transport it on an optical fiber, and then with a photodetector, the light beam on and off is basically translated into electrical current and therefore a digital signal again. Now that way you can scale to like 100 gigabit per second on one channel. How do you do that on a chip? Well, basically a transceiver chip in its simplest form looks a bit like this. So you have the laser, you have your modulator, you send it out through a fiber. At the same time, another fiber comes in with the return signal, and that goes to a detector. So that's a very, very simple circuit. It doesn't contain a lot of building blocks, but it does a very important job today in optical communication. Now, why does this work? So, well, one of the things that optics has, it's an electromagnetic wave, but compared to radio waves, which are sitting here between 0 and 100 gigahertz, optical waves are sitting entirely on the different side of the spectrum, typically around 200, 300 terahertz. So the amount of bandwidth that you have in the electromagnetic spectrum, you're struggling with getting as much radio signals onto a 5 gigahertz wide band. Here you have 40 terahertz communication bandwidth at your disposal. So the amount of information you can transport over optical fibers is massive. You just have to make practical use of these. And the way that we do it today, to make use of this 40 terahertz of bandwidth, is to chop it up into little channels, each channel having a bandwidth of 100 gigahertz, something that you can handle with electronics. And then basically just like we're used to old-style FM radio signals, each having their own channel, well, you have here all these communication channels, each using their own wavelength of light to transmit it, all over the same optical fiber. So a communication link basically becomes a bit more complicated. You now need a laser for every channel. Basically, every channel runs on a different color, a different wavelength of light. You need some multiplexer that combines all these wavelengths into a fiber. And then at the output, you need to basically separate all these wavelengths and send them all to your own receiver. That's how today the entire backbone of the internet works. So every bit of data that you send onto the internet and back goes through systems like this. All the long-haul submarine cables, they all run on this type of technology today. That way, you can go, instead of 100 gigabit per second, you can scale to hundreds of these channels. Petabit per second per fiber become possible. So that's kind of setting the scene, just what photonic integrated circuits are. Now what we are working on is programmable photonic integrated circuits. We don't want to use these circuits just for communication. We also want to use them for information processing and signal processing. And that's what this programmable becomes. How can we now program such a circuit, not just to transmit information, but to also process that information? Now, for that, let me just define some concepts here for clarity. If we talk about signal or information processing, when I talk about signal processing, I'm just talking about having a waveform coming in. There's some transformer object that processes that waveform and then sends it to an output waveform. It does not do any interpretation of the waveform. If we talk about information processing, we're trying to get some information out of the waveform. The most simple way is you get a light wave coming in, and at the output you have a series of zeros and ones. So kind of a typical digital receiver in an optical link. If we talk about computing, then we're really transforming the information. We're not transforming the waveform. We're doing an interpretation of the waveform, getting information out, transforming that information, and then, if necessary, generate it again on an optical waveform. So we can actually do all of these things with light. But today, the classical way of doing most of that processing is just very simple. It's digital signal processing. We take a very, very roundabout way to process a waveform. We get a waveform in, we discretize it, we basically chop it up into little bits. Every time slot is discretized, so we get a digital stream, which contains a lot of digital information. We run it through a digital signal processor that does all these arithmetics in the digital domain. And then at the end, we basically convert it back to a waveform that is transmitted on to the next station. This is very, very complex for quite a lot of operations. If this is, for instance, the Fourier transform, you have a lot of digital operations needed to do that Fourier transform. Remember that in optics, we could do a Fourier transform by just using a lens. So this is quite expensive in terms of power consumption for quite a lot of these operations, especially the ones that are listed here. Now, if you take a few steps back in time, before we had digital signal processors, if people wanted to implement filters or convolution, they did it in a different way. They basically used the waveform, split it up into delays. This is a very common techniques for radio engineering and acoustics. You split it up in different delays. You control how much amplitude and phase there is in every delay, and then you combine them again into a combiner. And because after these delays, every signal gets a different phase delay, you can get constructive and destructive interference depending on the frequency or the wavelength. So which means you can actually implement a filter, which is typically done in digital signal processing today. You can implement this entirely in the analog domain. No need for analog to digital converters, digital to analog converters. Of course, this is an analog system, which means that it's sensitive to noise, it's sensitive to losses, etc. So now, as I said, optics is waves, but also radio is waves. You basically have the electromagnetic spectrum, but because you have these waves, you can actually apply the technique that I showed here to optical and radio signals. Now, I already mentioned we can basically use radio signals and optical signals, and we convert them back and forth. We have these objects called a modulator and a detector, which can convert an electrical signal or a microwave signal into the optical domain, basically transporting the signal from this frequency band to the optical frequencies and back, and then use optical fibers or optical chips, optical filter circuits to process that information. The nice thing is here that what is a wide band for microwave becomes a very narrow band for optics, which of course, if you have, it's much easier to process a narrow band than to process a wide band. So the moment you transport a microwave information or microwave signals into the optical domain, a lot of processing functions suddenly become a lot easier. So if we look back at, this was our transceiver circuit, we can now actually add filtering circuits in this path. So for instance, this is an optical filter consisting of an interferometer with 4 resonators in it. You can, by taking that filter circuit, you can correct, for instance, for imperfections in your optical communication link. It becomes even more interesting if you just take the optical fiber out. And you basically just connect the laser, modulator, filter, and detector together in one path. What you now have is a chip that on the inside works with light, but it has no light coming in and out of the chip. The outside just sees a microwave, so an electrical signal going in, and an electrical signal going out. So what you have here is an optical processor which processes microwave signals. Now, if you make every function in that optical processor tunable, so you basically, instead of having a fixed configuration, you make sure you can control every splitting ratio, every phase delay in this whole circuit, you can now have a programmable microwave processor. And if you then add some other components to just get optical signals in and out, you now have a chip that can do optical signal processing and microwave signal processing in the analog domain on optical waves. And this is an example of a chip that was made at Ghent University and IMEC a couple of years ago. At the top, you see the input and output for the fibers. This is a modulator. This is a laser. This is a programmable filter, and then at the bottom you see all the interfaces for electrical wiring. And we can actually use this chip to now do both optical processing, like you send in an optical path and you send it back out to a photodetector. The chip now does not get electrical signals in and out, it gets only optical signals, but you can program the optical response. I have a bandpass filter, for instance, and a tunable bandpass filter for different wavelengths. You can program that in that chip because every element on that chip is programmable. You can do the same thing for microwave signals. So you can send a microwave signal in on that modulator and then use the optical filter to filter the microwave signal and convert it back into the microwave domain. And again, that works. You can do bandpass filters, you can do low-pass, high-pass filters, you can do equalization to restore, for instance, a bit pattern after an optical fiber link. Now, I use this as a very basic example of how you can make a chip programmable. This chip could already do optical filtering, microwave filtering, and if you put it if you add some extra components, you can make oscillators, you can make frequency converters. So it has quite a lot of functionalities already built in, except that even though you can tune every element, it doesn't do a lot more than that. So if we want to make chips really programmable, if we want to basically make sure that we can do more than one function with a chip, we have to look at slightly more complicated architectures. And that's where I introduce a second class of programmable photonic circuits, which I call the forward-only meshes. Some people also call it the multipath interferometers. What is it? It's an optical chip with a number of waveguide inputs on one side, a number of waveguide outputs on the other side. And what is connecting the inputs and the outputs is essentially an interconnected mesh of waveguides. And at every interconnection point, we have what we call a controllable optical gate. The optical gate is a very simple concept. It consists of two inputs, two waveguide inputs, two waveguide outputs. And inside the gate, we can control how much the two waveguides couple together, but also how much the optical phase is delayed from between the two outputs. And that is enough to basically define a unitary transformation between the input and the output. And it's basically mathematically proven that you can basically construct any unitary transformation as a cascade of 2x2 unitary transformations. So, to implement this, we only need two types of functions. We need an optical phase shifter, a phase delay, and an optical coupling that controls how much light is coupled between the two. That can be implemented in different ways. A common way to implement this is, again, our Mach-Zehnder interferometer, or simple interferometer that we had, with one phase shifter that controls how much coupling we have. And then if you add a second phase shifter, you can control the delay. Now, the nice thing about this architecture is that you can do already quite some interesting functions just with this simple component. Let's say we have a 2x2 gate, an optical gate with two input waves coming in. We don't know upfront what the relative intensity and the relative phase of these two inputs is. But we can now configure this gate to make sure that all the light that has been sent in the inputs ends up in output 2. And we don't have to do any computations for that. We just have to run very simple minimization algorithms. For instance, we put a detector at output 1. And now what we need to do is configure these two elements that we minimize the power in that detector. That's very easy. We can first control the phase here to make sure that the light that goes from output 2 and output 1 as far input 2 and input 1 into output 1 cancels out as much as possible. We basically make sure that they're in anti-phase. So by tuning that, we reduce the power in the detector. If we now use the same detector signal again, but now to tune the coupling, we can tune the coupling in such a way that the two contributions that end up in output 1 are equal, so they fully cancel out. And that way, no light ends up in the detector anymore. And because the rest of the system is lossless, that means the light has to go somewhere, it all ends up in output 2. So without doing any computations, any pre-configurations, any assumptions on what the behavior of these devices is, with a simple minimization algorithm, we can have a system that automatically adjusts itself to send all the light into one output. Now we can cascade these gates to build a system that basically does the same thing, but for 4 outputs. So you first run the optimization on the first gate and the second gate and the third gate, and as a result, everything will end up in output 4. And this is a self-configuring system. Again, it does not make any assumptions on the exact behavior of the gates and on the exact configuration of light that goes in. You can use this to make systems that perform a lot better than static systems in the real world. Like if you have a beam of communication, a laser beam between 2 buildings, there's always turbulence, so your beam will get disturbed. Your beam profile will change. If you only have one detector to read out the beam, then you might lose a lot of information. But if you use now multiple detectors, like multiple of these antennas, to capture the beam, and you combine them with a set of optical gates into one receiver, you suddenly get a much more stable system, because this system can adjust itself to air turbulence. And indeed, that's what we see. This is a chip that was developed by my colleagues in the Politecnico of Milan. They basically have 9 antennas arranged in this pattern, and then an optical circuit that combines everything into one receiver. And if you have this active control on, you see that the beam or the signal integrity remains fairly constant. You only have like very small dips in the received energy because of turbulence. If you switch the control off, you suddenly see that the intensity drops a lot, and you get a much higher variation into your output signals. So having, again, programmability in your system, having a way that you have electronic control and feedback loops in your system, gives you a lot of extra features. This is basically a reverse operation. If you can capture an arbitrary pattern of light and maximize the power in your detector, you can reverse the flow. You can start from a laser and then generate an arbitrary pattern of light. This is a very nice example of the colleagues in Zhejiang University who managed to generate different light profiles just from a chip like that as well. This is an example from MIT from already like more than 5 years ago, where you have a chip which consists of all these optical gates. If you zoom in closely, you can see the optical gates. You can recognize them. It has 26 inputs and 26 outputs. It is not used to, for instance, make a free space communication beam. No, it goes one step further. It's used to define an arbitrary linear transformation between a set of inputs and a set of outputs. And that is actually quite useful, because if you represent your waves at the input of such a system with a set of complex numbers, like A1 to AN, these are complex numbers because every wave has a certain amplitude and a phase. And the output waves are also a set of complex numbers with an amplitude and phase. What this circuit does is exactly the same thing as I showed in free space in the beginning. It performs a real-time matrix vector multiplication, a real-time linear transformation between inputs and outputs. It just takes the time of light to propagate through the circuit to perform this operation. And no digital computations are involved. Now, this is a very, very useful functionality, because matrix vector multiplications are at the heart of every AI algorithm today, of every pattern recognition, but also at the heart of all quantum computations. So if you can do this in a very efficient way, with low loss at room temperature, with a lot lower power than you do with digital electronics, there is a lot of useful things you can do with that. For instance, you can actually implement hashing functions. So certain crypto mining or Bitcoin or blockchain algorithms can be massively accelerated using these optical circuits. Other ways that to do, you can use it to train neural networks. You can even run back propagation inside such optical systems and train them to execute specific neuromorphic operations. There's companies like Light Matter and Lightelligence who are actually actively building systems based on this kind of a principle. So accelerators that you can plug into your computer to perform matrix vector multiplications at a much lower energy cost than you would do with electronics. You can also do it for quantum. Basically, a lot of operations in quantum computing require linear transformations. So if you can represent your qubits as photons, single photons typically, you can then use that to operate, to perform, to implement linear quantum gates. Operations like boson sampling, etc., can be done very easily on such photonic circuits. Again, quite a lot of companies are now actively involved in building systems based on this type of photonic circuits. Now, I said this was the second class of programmable photonic circuits. I'm still not happy with it, because even though you can do an arbitrary linear transformation between inputs and outputs, that's the only thing you can do. That's an arbitrary linear transformation. There's more to photonics than that. So what can we do? Well, the next class that I introduced is called recirculating meshes. It basically tries to compensate some of the shortcomings of these forward meshes, given that the forward meshes are usually made to work on every wavelength, so they can't do wavelength filtering. They don't have feedback. The light only propagates in one direction. It doesn't loop back into the system. And they can't do programmable delays, which are all elements that you would need if you want to really process time signals. Like in real-time integration, real-time differentiation is not really easy to do with these type of circuits. It was easier to do with the first type of circuit I showed, but not with these. So can we combine the best of both worlds? Can we get the functionality of our microwave processor that I showed earlier with the kind of programmable meshes that I showed next? And the solution is to make a kind of waveguide mesh instead of input to outputs, is basically make a waveguide mesh that can couple all ports together. And the way to do that is quite simple. We need the same type of optical gates that we used before, except that now we organize them into loops, not into a forward topology, but into loops. So that can be square loops, that can be hexagonal loops. But this way you can couple every port to every other port, because the light can just circulate in this mesh arbitrarily depending on how you program each of these gates. How does this work? Well, if you take the two extreme states of the gate is either in 0 coupling or 100% coupling, and you just use them as a switch, you can reroute the light in any path through this mesh. You can even route two paths of light through the same mesh. Now it becomes more interesting even if you can not only configure these gates in bar or cross, but you can also configure them in a partial state. So in this case, you can split your light over multiple paths. You can do signal and power distribution. But if you can split, you can also use them to combine signals of light. And now this is interesting because what we've built here inside our waveguide mesh is an interferometer. We split the light over multiple paths and we let the waves combine in a programmable way. And if one of these paths now introduces a delay, we're back to one of the primary components that I started out with, or Mach-Zehnder interferometer that we can use as a wavelength filter. And so this is a circuit where you can program wavelength filters. It's a circuit where you can program delays. You can split light over multiple delays and combine them again. Again, remember that was kind of the basic functionality of signal processing that we started out with. You can also do it in resonators, so you can run the light into loops. You can build these ring resonators with these sharp resonance transmission bands. So you have all the basic building blocks to make both finite impulse response filters and infinite impulse response filters and combine them together in a programmable way. Now, the first implementation of such a system was done in 2017 by two of my co-authors, Daniel Perez and Jose Capmani. They built this kind of 7 unit cells of a hexagonal mesh that they could then program to perform a number of these functions. This is another example of such a mesh. This was a bit later. It's from my team in Ghent University. It's a bit more compact, but it has this similar 7 unit cells of a hexagonal mesh. And indeed, if you combine that photonic chip, which is here at the top, it's hidden under basically a layer of glue, so it's very hard to make out the chip, but it's a few millimeters across. It needs quite a bit of electronics to run, because all the elements on the chip need to be electronically controlled. But then if you take that chip, you can indeed make a resonator in it. You can run the light around in a loop. You can do splitter trees, like coming in from number 17 here and then splitting out over 8 outputs. and you can balance that power. You can make delay lines, so basically by just configuring longer paths through the mesh, you can basically delay light with a controlled amount. And you can program more complex filters, like you can combine two rings together into a second order filter, or even two Mach Zehnders together into a second order, no, this is a third order filter actually. Or in this case, this uses most of the mesh together. It uses 4 different rings and a Mach Zehnder, very similar to the function I showed in our first chip, that you can now implement just by programming. So you don't have this hardwired in the first place. You basically program this functionality into the chip. And this is interesting because you can now use this chip for a filtering operation, a power splitter, a delay line. Depending on what you want to use it for, you can just reprogram it for different functions. Now, there's a couple of constraints here, of course. I mean, this is a programmable device, but of course you cannot program any delay in it. You can only program multiples of that unit length that is used to define the circuit. And in order to be able to process microwave signals, you need to have a sufficient bandwidth of your filters to be able to process high-speed microwave signals. And that comes with some demands. Especially, you want to keep the length of that unit cell as short as possible, which is quite a technological challenge to do in photonic circuits, making these things small and short. An intermediate solution would be to break the regularity of the mesh. This is something that in this particular field is only starting to happen now. All the demonstrations up till now used a perfect hexagonal mesh, but here you have some early examples of irregularities, defects that you introduce in the mesh that actually allow you to basically create shorter paths or create wider spectral bands for your photonic circuits. This was done by the Politecnico di Valencia from the group of José Capmany, where they basically, you see that they introduce shortcuts in the unit cells that give you different delays than the ones that you typically expect from a regular unit cell. Now, building a larger circuit or a larger chip out of such a waveguide mesh only gives you the linear operations. It gives you the filtering, it gives you the Fourier transform if you want, or linear combinations. It doesn't give you all the other optical functions. For that, you need to, of course, add additional functionality at the input and the output. So you need modulators, you need photodetectors, and maybe some other functional blocks that you can add at the periphery, like amplifiers or dedicated filter circuits. Now with this, it becomes quite interesting because now you have a chip that can do most of the things that we wanted to do up front. We have fiber pores that connect to the optical waveguides to the outer world. You have modulators that can take in a microwave signal and convert it into the optical domain. And you have your photodetectors that can take an optical signal and convert it back into the microwave domain. So, and you can arbitrarily connect them together using this mesh in the middle. So this comes very close to what we could call a general purpose photonic chip. And again, it's all powered by these simple optical gates that we started out with. Now, to make this into something that's useful, that takes a bit of extra work. You cannot just start with the optical chip. You need, for every element on the chip, you need some digital and analog electronics to control everything. And you need a software layer on top of that to make everything work. So a system would start to look a bit like this. Packaged together, you have your photonic chip, you have your electronics on top of that, you have some digital control. You need some packaging to have good connections to your microwave inputs and outputs. And then you need your optical fibers to be connected to the optical ports of the chip. And of course, a laser source to make everything work. Now, all of that together is just the hardware. And this is something where our paper and our work really starts to make a difference. What we wanted is a programmable photonic chip or programmable photonic circuits. Photonic circuits, like with this hardware, have been around for some time, but they haven't been programmable. We now need to add software layers, which is a completely new domain for photonics, is to define the photonics in software. So you need to have control loops, you need to have configuration algorithms, synthesis algorithms, and even development tools for people to play with these chips. And that's a very, very new field. So coming up with the software layers that do both the design of the chip and the configuration of the chip, can control the hardware and can also do some simulation of the chip, that's that's a work in progress, and at this point, it's still at a very rudimentary level. It's like programming a computer chip in machine code. Now, software, it does exist. You can already program these chips, but it's at a very, very basic level. It basically allows you, instead of designing chips as a geometry or designing it as a set of building blocks, you now have a chip that is already there, and you design by setting the states, or controlling the states of every individual element in that chip. So you get the functionality you want. But again, at this point, at a very, very basic level. We are working at higher level routines, and for that you need a mathematical representation of the chip, a kind of a digital twin inside your computer to run these higher level control routines, which typically means you need a graph representation that also very accurately captures the physics of the device and the allowed flows of light. And then you can run a lot of the existing network configuration or traffic management algorithms that are already existing running on graph representations. Like, for instance, in this case, we define 8 different paths at the same time without collisions through the mesh. This is another example where we use linear integer programming to basically configure a waveguide mesh to perform a 1x6 splitter, but with different constraints. Here we want to use as few gates as possible to do the splitter. Here we want to split the light as quickly as possible, so to distribute the power as much as possible over the chip. Or we use really pure optimization algorithms to configure a chip. In this case, we randomly initialize a mesh, and then we try to approximate this particular filter behavior in the mesh by just local optimization, a kind of a steepest descent method. So let me check how much time I still have. I'm almost running out of time, but I'm almost okay. But that I can do. That's okay. So last question: is this actually something useful that we can do with programmable photonics? Well, what I started out with was to be able to do information processing, signal processing with light. But I really want to do that for as many applications as possible. So something I need is a programmable chip that we can reconfigure in software to perform all these different functions. Not just optical interconnects, which is the current economic driver for photonics today, but a lot of different applications. It's like saying that if we only wanted electronics for calculators, we would not have the richness of our world today. Electronics is used everywhere in a lot of different applications. Photonics today is mostly used in optical communications and not much else. You can't buy a lot of other products containing photonic chips today. And that needs to change, and that's also where these programmable photonics can help. Because if you project the market for photonics, there's only a few things that have not to do with communication. We want more than that. We want photonics to be a technology that can not just be used in data centers and optical fiber links, but that can also be used in the house for routing information in the house, that is used in cellular networks, but also in sensors like monitoring your buildings, monitoring bridges, controlling your car, LiDAR for self-driving cars. All can work on photonics and can all be based on these photonic chips. So if you can do this general purpose signal processing in photonics, these applications become a lot more interesting and can be a lot more useful and find their ways in a lot more places, which I think is good for the technology as a whole. So getting to photonics in all these other applications is something where we think programmable photonics can help a lot, because it can help you speed up your developments, speed up your iterations. Instead of having to do iterations in design and chip, you can do it with rapid prototyping. Just like in electronics today, we do that. Just to sketch you why this is important, if you want to do a new photonic chip today, it takes you a year. If you can do a chip, you can take a programmable photonic chip and you develop in your programmable photonic chip, it takes you a day to get a new prototype working, because it's just changing the program of the chip, not changing the chip itself. And that's what people in electronics do today with FPGAs and digital signal processing. They are in this cycle. In photonics, most people are in this cycle. So if we can basically enable this type of development cycle for photonics, we can also enable all these applications. So it has an economic, it has a potential to really have a large economic impact as well. There are some drawbacks, just like in general purpose electronic chips. These can be more expensive, they can have higher power consumption, but they have all that flexibility that makes it possible to basically go much faster in development time. It can save you a lot of time to try out a new application. It also makes everything upgradable, and it also gives a software interface, which for people who do not know the technology itself, they can still program it, they can still do something useful with it. And I hope that will really make a difference in the future. So if I go to my summary, I think that the technology that we kind of created a vision for, created perspectives for 5 years ago in our paper, really has progressed quite a lot in those 5 years, but it's still not there. We're still at a state where this has to prove itself. Today, photonics is only used in data centers as a real commercial application, but the potential of photonics has been shown already quite strongly in other applications in academia. And I hope that programmable photonics can help people to translate that potential from academia to industry and really make photonics a useful technology for much more than optical communication. And with that, if you want to read more, there's the Nature paper that we published 5 years ago. There's also this book by my colleagues, Kapmani and Perez, and some other papers that could be useful. Thank you.
Thanks, speaker, for the nice talk. So any questions or comments? Okay, please.
I was fascinated by this topic. So, your opinion, what do you think? How long could it take to really apply this for signal processing? As you said, I mean, you know, this stuff about trying to program and to introduce the software layer on this. I mean, in your experience,
for really general purpose image or signal processing, it will take some time, but already we see that, like, for instance, in fiber links, they are already putting some optical signal processing just before the detector, like to compensate for imperfections in the link. That's already happening. Then there's companies like Lightelligence and Light Matter who are actually putting some products on the market, early generation products, to do these matrix vector multiplications as an accelerator for neural networks and image processing.
Oh, great.
This is still early days. Putting a timeline on it exactly when it will really become mainstream, it's very hard to tell, especially those general purpose processors. My personal timeline would be like 3 to 5 years for that to become like really on the market as a starting point, and maybe like 10 years before it's really kind of an adopted technology with a large community around it.
I think it should be really great to be there, you know, looking at this change.
Oh yeah.
I mean, because we are really working on this topic, so you know, you see that everything is lab and then it becomes production. I think it's really
and it's
exciting.
Also, and it's when you look at it on short term, it all seems to move slow, and then suddenly you're 5 years later and you see all the things that have happened in those 5 years. So it's very, very hard to kind of.
When I started my PhD, I remember some colleagues talking about, you know, these neural networks, and they said, "Oh yes, very interesting, but you know, they cannot be implemented." And then in 10 years they were there, and there was this revolution. So you know, it's important to keep working on this stuff.
And this is a type of what you call a bootstrap technology. Like I said, it now takes a year if you develop a new optical chip. And for developing these programmable photonic chip at this point, it also takes us a year for each iteration. But if it really works, then suddenly it accelerates because you can start iterating in the same technology.
Yeah, I agree.
So the moment we have a device or a system that is good enough to start building on itself, it could accelerate very rapidly. It's very hard to tell when exactly that.
No, clear. Thank you.
So we can have a quick question, please.
Yeah. For large-scale integrations of the devices like Mach-Zehnder interferometers, phase shifters, MMIs, is it like requires to calibration the device like one by one?
Yes.
And is it possible to do the MPW project in IMEC from the Chinese, like, for example, research institute?
Okay, that's two questions. So first one is, how does this work to calibrate such a system? Yeah, so that to clarify, yes, these are analog systems, and there is always fabrication variation. So a circuit like that, every gate will be slightly different compared to the other gates, which means that you need, in order to configure such a system properly, you need to calibrate every gate. Now, luckily, the calibration routines are actually already fairly well established. So it is, for a variety of these circuits, we can actually calibrate to a very high precision these circuits. It takes a one-time operation to do it. And depending on the speed of your electronics, that takes between, let's say, 30 seconds or a few hours. But it is possible, and it doesn't need to be done regularly. It can be done once. So the calibration, I think, is a problem that is maybe not 100% solved, but at least solvable. Now, the second question, can you actually have such a chip fabricated in IMEC for a Chinese student? That's a very tricky question to answer. It depends. In principle, the IMEC multi-project wafer services are open. But I don't know the exact policies when it comes to export to China of such chips, and what the restrictions are on which institutes can actually participate. I don't know. I don't know by heart.
Yeah,
so I cannot
other,
really
like,
give an answer.
foundries, but I think IMEC is one of the best.
IMEC is indeed one of the better foundries for this type of technology. That's true.
Thanks.
Okay, let's thank the speaker again.
Thank you.
And we will have a 15-minute tea break. And I don't know where we can find the snacks.
Ah, okay.
We